All right, this is day 14. We are talking more about probability this week. We'll be talking about probability going into next week as well. And just to mention this again, we are spending this time talking about probability. This is a statistics class, not a probability class. We're talking about probability because we're going to need it moving forward when we're talking about inference. So the big statistical questions are, if we run some experiment, what can we say about the results that we see? Well, because of the way randomness works with experiments, we need to be able to have this language of probability, this language of likelihoods, in order to talk about the results that we can get from an experiment. Okay, so that's sort of big picture why we're talking about this now. Like last class, we're going to be spending a fair amount of time today talking about some vocabulary terms, just because we need to make sure that we're on the same page moving forward. Okay, so to start off, we say that a trial is an instance where we are sort of testing our probability. So I like to think of, so common examples for this would be things like coin flips, free throws. I'm saying like either you make or miss a free throw, dice rolls. The list goes on and on. But we're going to be focusing on those three for a fair amount. So when you do one of these things, one of a certain number of outcomes occur. So we say an outcome is one of the possible things, or one of the possible outcomes. For example, if we were talking about flipping a coin, that's a trial. The heads would be one outcome and tails would be another outcome. So we say that the sample space is going to be the set of all of the possible outcomes. So for example, if the trial that I was running, if the instance that I'm measuring is rolling a die, then the sample space is going to be the set of all the possible outcomes. Well, it could be a 1, 2, 3, 4, 5, or 6. I'm assuming it's a 6-sided die. Okay, so that's the sample space. We're then going to say that an event is some collection of outcomes. It's some subset of this sample space. So an example of this might be, if we're again talking about a die roll, then let's say that our event is going to be the set 2, 4, 6. All right, so when we're talking about events, we can describe them, we can often describe them in multiple ways. In this example, I can just list 2, 4, 6, or I could specify that A is the set of even results. All right. So we can point to, we can talk about a particular event, a particular set of outcomes in a number of different ways, and it's totally valid to do one way or the other. All right, and so this is actually enough for us to start to be able to say sort of our first probability formula, and that is that, well, if we've got some event A, like let's keep in mind the event where the result of the die was something even, then we can calculate the probability of that event occurring by just saying, all right, it's the number of things, number of elements in A. So in this example, that was 3, divided by the number of elements in total, so in the entire sample size. In other words, the probability that a die roll is an even number is going to be the number, the count of even numbers divided by the total number of things that can happen. So obviously this is 3 over 6, or 1/2. So I think that should hopefully agree with everyone's impression of what the probability of getting something even off of a die roll. But this is sort of a more formal way of writing down where this number comes from. There's one big caveat here. This only works if all outcomes are equally likely. If we're talking about rolling a die, assuming that it's a fair die, we can say that each of the individual results, should have about the same weight, about the same probability of it occurring. We might say that there's a 1/6 chance of each of the possible results. So then when we do something like this, what we're doing is we're adding up all of the 1/6 that are relevant, right? We say it's 3/6 because, hey, there are 3 of the total pieces that, 3 of the total possible outcomes that fall into the category of the event. Where this logic wouldn't work is if the outcomes are not equally likely. For example, let's just say that some basketball player is taking a free throw shot, and the result is either they make it or they miss. Well, typically, free throw shooters, if you actually play basketball, your probability of making it is probably greater than 50%. If you don't play basketball, like me, it's probably a little bit less than 50%. But typically, it's not going to be 50%. Making and missing it are not equally likely events. So because of that, we can't use this logic at all. Okay. One example that we're going to use a lot moving forward, because it's very conducive to talking about probability, is sort of the standard deck of playing cards. So just to recap, for those of you who aren't necessarily familiar, a deck of playing cards has 52 total cards. We're going to have 4 suits: spades, hearts, diamonds, and clubs. Spades and clubs are considered black cards, while hearts and diamonds are red. And so each of the 52 cards is one of these suits. It's also a rank. So it also either says A, so meaning that it's an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, or king. So there are 13 of these, and 13 times 4 is 52. So there are a total of 52 cards. Each one is a unique combination of a suit and a rank. Right. Let's revisit the addition rule that we talked about last time. So last time we said that if we are talking about the probability of A or B occurring, then we can add the 2 probabilities together. And there was one important caveat that we're going to discuss now. So let's revisit this with this particular question. If I draw a card from this standard deck of playing cards, in other words, if I select one of the 52 cards at random, then what is the probability that the card is either red or an ace? All right, so let's split this up. Let's say the probability of red or ace, well, let's find the probability that the card is red, and separately let's find the probability that the card is an ace. So if I want to know the probability that the card is red, one thing I can think about is, well, how many red cards are there? If there are 13 hearts and 13 diamonds, then there's a total of 26 cards that are red. So 26 divided by the total number, or 52. Or you could just recognize that, hey, half of them are black, half of them are red, so 1/2 are going to be red. Cool. Separately, if I want to know the probability that the card is an ace, there are 4 out of the 52 cards, or 1/13 of the cards are aces. So the addition rule I mentioned before, or that we talked about last time, said that we can just add these things together. So there's a problem with this, because here we are counting up how many red cards there are, and here we're counting up how many aces there are. And we've actually counted the ace of hearts and the ace of diamonds in both of these categories. So if we were to just add these numbers together, then we might be led to believe that there are 30 red or ace cards. And when in reality, there are actually, should only be 28, because we are double counting 2 of them. So the way that we're going to adjust for that is that we're going to subtract off the probability that we have a card that is both a red card and an ace. So in practice, what that's going to be is, all right, how many cards are red aces? Well, there's the ace of hearts and there's the ace of diamonds. That's 2 of them over 52. In other words, 1/26. So then this is going to end up saying that our total probability should be 1/2 plus 1/3 minus a 26th, or it's actually easiest if we leave them in terms of 50 seconds. We end up with 28 over 52. We could have also gotten here by just counting up. So we have our total of 52 cards. We can just go sort of the direct route and say how many of them are red or aces. And we could have added them up that way. So maybe we have 13 red, 13 hearts, 13 diamonds, and then adding up the 2 additional should also give us the 28. Cool. The reason that I wanted to walk through this was that I wanted to point out the structure of this formula, because this is the generalized addition rule. So the rule is that the probability of A or B, that's just going to be the probability of A plus the probability of B minus the overlap. Right. And the reason we have to subtract out we have to subtract off this part is because this is the portion of the probability that we're double counting. All right. So I actually find a picture for many, many things in this class. A picture is a great idea. So I think a Venn diagram can help capture what's happening here fairly well. So if the left circle is representing A and the right circle is representing B, if I want to talk about A or B, then what I mean is I want anything in any of this. So if I were right here, then would I be in A or B? Yeah, because I'd be in B. If I was here, I'd be in A. If I was here, well, I'm in both, so I'm definitely in at least one of them. Right. So when I want the probability of A or B, what I want is, in a sense, this region. All right, so this is sort of a graphical reasoning for why this equation works. And the idea is that if we have A or B, that should end up being the same thing as, well, if we just had A, that's going to be the left circle. If we just had B, that's the right circle. And if we added those 2 circles together, well, we've double counted the middle. We've double counted A and B. So we can actually account for that by subtracting it off. So if we sort of did this pictorially, we've got our left circle plus the right circle minus the overlap, because we've in total so far counted 2 overlaps. If you subtract off one of them, you've got one of those middle pieces. That collectively should be the shape in question.